If you like the video, please subscribe Technical PCT channel and click the bell icon to get the latest videos.
In last class, we discussed what is the torque acting on a dipole, what is the potential energy of the dipole in uniform and non-uniform electric field, and what is the time period of oscillation of a dipole in uniform electric field, right? Just we recall those formulas. Torque acting on a dipole, PE sin theta, potential energy of the dipole minus PE cos theta, and work done to rotate the dipole PE cos theta 1 minus cos theta 2. Angular speed or angular velocity of the dipole when it is oscillating in a uniform electric field, root over PE by I. Then time period of oscillation of the dipole 2 by root I by PE, right? These we discussed in the previous classes. See, torque acting on the dipole, PE sin theta. Sometimes they ask this torque in vector form. Because torque is a vector. As it is, its magnitude is PE sin theta. Torque is P cross E. P is a dipole moment vector. E is the external electric field vector, right? P cross E. Once it is a cross product, the torque direction is direction of torque is perpendicular to plane containing P bar and E bar. Already we studied in our first year how to find the direction of the torque, right? U, potential energy of the dipole, minus PE cos theta. See, this is cos theta. Cos in the sense P dot E. It is a dot product of P and E, right? So torque, as it is a cross product, we know it is a vector. Potential energy, you know, it is a scalar. It is the dot product of P and E, right? Work done. It is also a vector. See, when it changes from position theta 1 to theta 2. One important point here to remember. If this is the field and this is dipole, making an angle theta 1 with the field, and it is rotated to another position, making an angle theta 2. This total angle with the field is theta 2. Then work done is PE cos theta 1 minus cos theta 2. Remember, always these angles made by the dipole with field direction. With field direction, right? We have one problem. Initially, the dipole is making an angle 30. This dipole initially at a position making an angle 30 degrees with the field direction. Well, it is rotated further through an angle 30. It is rotated further through an angle 30 degrees. What does it mean? Initially, the dipole is like this, making an angle 30. From here, it is rotated further, making an angle 30. So what is the total angle with the field? Once it is rotated further, theta 2, theta 1 plus 30. From here, it is rotated to an angle 30, given in the problem. So theta 2 is equal to theta 1 plus 30. That is 60 degrees, right? So just they may ask, first question, at first position, what is potential energy? At the second position, what is potential energy? And what is the work done? They may ask. What is the potential energy at the first position? What is the potential energy at the second position? And what is the work done to rotate? Work done to rotate. Potential energy at the first position. If P is known, E is known, PE cos theta 1. At the second position, PE cos theta 2. Here theta 2 is 60. Generally, we commit a mistake here, right? Taking this theta 2. Work done, you know, PE cos 30 minus cos 60, like this. See, one important problem it is. Come on, note down. Well, we'll see the next problem. At what angle, at what angle torque equal to potential energy? Torque equal to potential energy at what angle for the dipole? When it is in uniform electric field, right? At what angle? See, torque formula is what? P sin theta. Potential energy minus PE cos theta, right? So where those two are equal, if you are asked, just equate these two, you'll get the answer. So where sin theta is equal to cos theta, just substitute the values, you'll get it. Okay? Sometimes they ask, this is the question asked in the previous sentence, magnitude of torque is equal to magnitude of potential energy. In the last Sunday also we asked the question. So magnitude of potential energy, PE cos theta. Magnitude of torque, PE sin theta. Then sin theta by cos theta is equal to 1. Tan theta is equal to 1. Here clearly I am mentioning magnitude of torque is equal to magnitude of potential energy. Sometimes they don't mention tau, magnitudes, the word they don't mention. Then in that case, simply take T is equal to U and try to solve the problem. Next. Like different models they design. Torque, half of the potential energy. At what angle? Like different relations they give, they ask different problems related to that. Important models. And when we come to here, time period. See, if you know time period, you can write frequency of oscillation also. Frequency of oscillation of a dipole in uniform electric field. What it is, we know frequency is reciprocal of time period. 1 by 2 by root over PE by I. You need to remember these formulas for solving the problems related to dipole in electric field, right? Okay. See, there is an electric field E. In that electric field, the placement dipole, it is in oscillation. It is making a small angle theta. Small angle theta, it is in oscillation at a particular instant of time. This dipole is here. This dipole length is given as L. Dipole length is given as L. As it is a dipole, mass of the two charges, M and M, mass of those two charges given as M. Dipole length is L. It is in oscillation in a uniform electric field. The question asked is, what is time period? What is time period? Right? What is the formula for time period? Time period is equal to 2 by root I by PE. What is I here? Moment of inertia. And P, dipole moment. E, electric field intensity. So if you know I, T values, if you substitute it there, you'll get the answer. See, what is I? See, this is the dipole. It is a two-charge configuration, rotating about its center. It oscillates about its center. As it is oscillating about its center. rotating, axis passing through this center, mass is m, mass is m. From here, what is the distance? L by 2. From here, what is the distance? L by 2. Because dipole length given for us is L. Then what is the moment of inertia? Moment of inertia I. Moment of inertia of this charged particle and this charged particle. For this m, we know the formula. Moment of inertia is mass into distance square for a particle. Here this charged particle, it is a small charge means charged particle whose mass is m, distance is L by 2 whole square for first one. For the second one also, m into L by 2 whole square. So 2 m L square, 2 square, 4, 2. So m L square by 2. This is moment of inertia of that charge configuration, right? For this charge configuration, this is moment of inertia. For this charge, m L by 2 whole square. For this charged particle about this axis, m L by 2 whole square. Total is 2. M into L square by 4, m L square by 2. I got. Then what is P? P. Dipole moment. Dipole moment P. Formula is what? Q into distance between the charges. Here in this particular case, L. Whenever you are given problems, in the problem see that the distance between the charges, that is L. So for finding dipole moment, magnitude of either charge and distance between the charges, right? Q into L. Now what is time period? 2 pi root. What I we got? ml square by 2. P is QL E. L, 1L, cancel out. And finally, time period, 2 pi root ml by 2 q e. This is time period, right? One of the problem asked in previous entrance. Come on, note down. Next. Next one. We move on to a new topic. Area vector. Area vector. Very simple topic and very important topic to remember for solving so many problems in electrostatics, electromagnetism, and magnetism, current, electricity, we need to know what is the area vector, right? Area we know very well. What is area vector? The vector whose magnitude is equal to area of the surface and direction is normal to the plane of the surface. The vector whose magnitude is equal to the area of the surface and direction is normal. Normal in the sense perpendicular to the plane of the surface is known as that planes or that surface area vector. Right? As you said, it is a vector, it should have direction. Right? So this is the note point to remember. Normal to the plane of the surface. Right? We'll see the example. Here I'm taking a frame XY coordinate system. In this is a plane. This is a plane which is in XY. This is a surface whose coordinates are A and A square surface. For this, what is the area vector? If you are asked, what is the area vector? From the definition, its magnitude is equal to the area. So area vector we represent like this. A bar. What is the area of this surface? It is a squared one. Sides are A and A. Area is A square. Okay. So this is magnitude of this area. And what is the direction? Direction is normal to the plane of the surface. So for finding what you have to see in which plane it is. It is in XY plane. If you draw the normal can be like this, outward normal or inward normal. Normal for the XY plane. What is the normal? Z axis is the normal, right? For this XY plane, this is the normal axis. Means we represent like this. This is the normal. Like. So for this XY plane, normal is Z. So it is in what direction? It is along Z direction. So how we represent? Into K cap. Why K cap? K cap is the unit vector along Z direction. Right? Okay. Or you may get that out. Why can't I write A square minus K cap, sir? You can. It may be outward normal or inward normal. See, this direction may be along outward normal or inward normal. Here I am talking about planes. Planes, generally we call it as open surfaces or 2D surfaces. These are called open surfaces, right? Or two-dimensional surfaces. For two-dimensional surfaces, this is the way. of writing. Okay. Magnitude, direction is normal to the plane. While taking normal, it may be a outward normal or a inward normal, right? Another. In this is the plane. This is the plane. This plane I consider. For this plane, let A and a square plane, square surface. What is the area vector of this two-dimensional plane surface for this, right? So what we had to see, area vector A bar, magnitude is A square. What is the direction? For finding the direction, what we had to see, in which plane it is. It is in XZ plane, right? This whatever surface we took is in XZ plane. If it is in XZ plane, what is the normal? That normal is along y-axis. Along y-axis, right? A square J cap. A square into J cap. Why J cap? Normal is along y-axis, right? Into J cap. Or A square minus J cap, right? Another. This is a circular disc. Circular disc. It is a circular disc whose radius is R. Whose radius is R. What is the area vector of that circular disc? This is the question, right? What is the area vector of that circular disc? Come on. Area vector A bar. Area of this disc. It is a circular disc whose radius is R. Pi r square. Then what is the direction? What to see? In which plane it is? It is in XY plane, right? It is in XY plane like this. Then what is the normal? Normal along Z axis. Here, see X, Y, Z I take, right? In which plane it is now? XY plane. It is in XY plane. Then what is the, in what direction it is? Along Z direction. So K cap. K cap, right? Or even you can write pi r square minus K cap like this. Okay. In general, if you observe all these, if I take this is origin O, this is A, and this is B. If this is one vector OB and this is one vector OA, then what is the area vector by using these two vectors? Right? See, come on, note down this. Well, what I get here? Let there is a vector along this direction. OA. And there is another vector along this direction. OB. What is the plane formed by these two vectors? What is the area vector of the plane formed by these two vectors? Plane formed by these two vectors. Let OA is given as A, OB is given as B. This is A and this is B. Generally, what formula we have for area vector? Area vector, magnitude of the area, A into B, right? And direction is normal to it. Normal, this here it is Y and X. Normal in the sense K cap. Can I write like this? AB. A is OA. B OB. OA. OB. Sin theta into n cap. What, sir? Why you got like this? See, OA, OB sin theta into n cap. Is it not? OA cross OB. Is it not OA cross OB? This is one vector. OA, OB sin theta into n cap is the formula for OA cross OB. Right? The direction of the cross product is always normal to the plane. Whenever different planes are given to you by different sides, if you want to find the area vector, apply this. Right? If they are regular, one is along y and one is along z, immediately you can find it is along x and y, this is along z. You can easily find out. But if planes are in different ways, in high-end problems, we need this formula, right? Remember, if two vectors are given to you, by using those two vectors, a plane is plane. The area vector of that plane, OA cross OB, simply, right? See here, OA cross OB. OA in what direction? Y direction. So I can write OA in Y direction. A J cap. Okay. OB in what direction? X direction. Cross A I cap. A I cap. Okay. What is the cross product of J and I? That is minus K. A into A square minus k cap. So it can also be written as OB cross OA. If you take OA cross OB, it results minus k cap. OB cross OA, it results k cap. K cap means outward normal, minus k cap means inward normal, right? Okay, come on, note down. So these are for open surfaces or 2D surfaces for planes. What is the area vector? This is the case. Next, for closed surfaces, what is the area vector? How to consider the area vector? Closed surfaces means what? We'll see. See, one note point to remember is we use this area vector concept in the calculation of flux. It comes tomorrow. What is the note point? You may get it out. Sir, which one we had to take? Outward normal or inward normal, sir? Which we had to take? When we are doing problems, consider the area vector direction, which is in the direction of the field. When calculating flux, consider A bar direction in the direction of field for 2D surfaces, not for all. For these open surfaces or 2D surfaces. Tomorrow, whenever we are discussing flux, we come to understand. Okay? A bar direction is in the direction of the field. For 2D surfaces. Tomorrow we discuss it. Next. For 3D surfaces. 3D surfaces are closed surfaces. 3D surfaces are closed surfaces. Till now we discussed two-dimensional surfaces. We call them as planes. 3D surfaces. One simple example. A cube, a simple cube I am considering, right? If I I take it in a coordinate system, it is in this coordinate system, right? X, Y, Z. Okay. Now I am taking names of the planes. This is plane 1. This is plane 2. This is plane 3. This is plane 4. And other these two planes, 5 and 6. I hope you understand. For a cube, there are 6 planes, right? I'm taking this is plane 1. This is plane 2. This plane is plane 1. This plane is plane 2. This plane is plane 3. This plane is plane 4. And other two we cannot draw. This side, that side, and this. This plane, what is the area vector? See, I said it is a cube of length A. Here cube length is A. Cube length, side length of cube is A. Side length of the cube is A. Okay? Now, what about these planes? 1 and 2 planes. Plane 1, plane 2. What these two are? See which planes they are. This is plane 1. It is which plane? XY plane. This plane is XY plane. This plane is also parallel to this. This is also XY plane. Right? XY plane. Clear? What about 3 and 4? Plane 3 and plane 4. It is formed by these two. Which axes are? Y and Z axis. Y and Z axis. Right? Right? Which planes they are? YZ plane. YZ planes. What about this 5 and 6? 5 and 6. Plane 5, plane 6. XZ planes? Yes or no? Simple. You take a room, right? In the room, this is x-axis, this is y-axis, this is z-axis, right? This side is y-axis, sorry, x-axis, this is y-axis, and that is z-axis. This lower surface on which I am standing, upper surface, these two are parallel. They formed by the axis x and y. X and y. If I stand, I am standing here. So for me, this plane and this plane are xy planes. That plane and this plane, that side plane, formed by y and z axis, right? So they are yz planes. For me, side planes. This side, and this side for the person. These side planes, YZ planes, and the remaining in which both is present and it's parallel, another wall, another plane. They are formed by what and what? X and Z, XZ planes. My question is, what is the area vector and its direction? We know area vector should always be normal to the plane, right? Tell me now, if it is xy plane, what is the area vector for that plane and for this plane? So xy planes, plane 1, plane 2. What is the area vector for this plane? Magnitude is a square. For this also magnitude is a square. Right? Direction is what? See here, this is the direction. For this upper one, this is the direction for lower one. Right? Plane 1, that is minus k cap. Is it okay? Normal outward. As it is xy plane, see, simply you can write. If it is in xy plane, another axis, z axis, unit vector, minus k because it is downward. For this, see here, outward normal, k cap. Right? A small doubt you may get. Sir, why for this it is minus k cap? Why for this it is plus k cap? See here, it is downward normal, this is upward normal. Simply to say, for a closed surface, area vector is outward normal. For a closed surface, for any plane on the surface, area vector is outward normal, right? For any closed surface. Very important note point. For closed surface, area vector is outward normal, right? Is always outward normal. You cannot draw it for in this direction. You should not draw. For this, sir, I draw like this. You should not draw it. Always outward normal, right? Okay. Now for this plane surface, plane 3, plane 4, plane 5, plane 6. You can tell it simple in a single stretch. Which plane? YZ plane. YZ plane. Plane 3. Here. Negative side. Right? Plane 3. A square minus. Here YZ present means it is along x-axis. Area vector. Normal. But negative x-axis. Minus I. This is a square I. Plane, it is xz plane. XZ plane. XZ plane. So area vector is along y-axis. When it is in y-axis, this is outward. For 6, inward. Outward. J. Outward. I took this one 5, right? Okay. 5 outward and 6 inward. For this 6 inward, a square minus g. I hope you understand, and you just go through it tomorrow with some more examples with problems we discuss it. Nothing to worry. Again, it comes 2 to 3 times repetition. But one important point, note down. For any closed surface, area vector is an outward normal. But for a plane, It may be inward or outward, right? Tomorrow we continue this topic with some more examples. Thank you.